Okay, we're going to do an LU decomposition of this matrix. I've already done the first step, where I just multiplied the first row by 1/3. Yeah, I did that mostly for convenience. It's just going to be easier to keep track of the numbers. I could get upper triangular form without doing that, just leaving the 3 there and corresponding numbers. But especially since 2 of these numbers came out integers, I just decided to go ahead and do this to be a little more secure in my reduction. Okay, so then I'm going to get -1, -2/3, -1. Say -1, it's 1. Then I'm going to add this row to this row, giving me 0. Now 3 is 9/3, I add -2/3, I get 7/3. And then I add -1 to 3, I get 2. And then I have -6 to 3. Then I've got 1, -2/3, -1, 0, 7/3, 2. I could have multiplied through by 3/7 there to get a 1 here, but I'm going to live with that one. I'm going to add 6 times this row to this one to give me 0. Okay, 2 is 6/3. 6 times -2/3 is -12/3. So -12/3 and 6/3 is -6/3, which is -2, of course. Okay, and of course I could say 6 times 2/3 is 4, so I got a -4 here to add to the 2 here to give me -2 here. Either way, 6 times -1 is 6, added to 3 is 9. And then okay, and then what do I have to do? I have to multiply this by whatever number gives me 2 here and add that to this row. Well, in order to get 2 here, I'm going to multiply by 6/7, because 7/3 times 6/7 gives me 42/21, okay, which is 2. And of course, you know, things cancel out. The 6 divides by the 3 to give it 2, and so forth. So anyhow, we get 0 and 0, and then we multiplied by 6/7, okay? So we got to do a little bit of work on the fractions. 6/7 of 2 is 12/7. 9 is 56/7. So we have 12 and 56, which is 68/7. So if I've done my arithmetic correctly, let's at least assume that I did, there's my reduction. Now what are the corresponding elementary matrices? Well, E1 is okay, what we get when we do the same operation we did here to the identity matrix. Well, here we multiplied the row by 1/3. We did that now to the identity matrix. That was kind of an optional step. We could have dealt with the fractions, but chose to do it this way. Okay, then we just added the first row to the second. So that means to the identity matrix, if we add the first row to the second, this is what we get. Then E3 is what? Well, we added 6 times the first row to the third. So it's going to be 1, 0, 0, 0, 1, 0, didn't mess with the second row, but then it's 6, 0, 1, where we add 6 times the first row to the third row of the identity. And then we have E4, where we just added 6/7 times the second row to the third. And there's the elementary matrix that adds 6/7 of the second row of the identity to the third. Those are the elementary matrices, and now we can see that this matrix here is E4 times E3 times E2 times E1A equals upper triangular matrix, which is this one. So A equals E4, E3, E2, E1 inverse times U, which is, well, if we do the inverse of this sequence, as we've done a couple of times, has to change the order of these things. Okay? So if we want to get the inverse of the product E4 down through E1, the inverse would be this. Because if I write this on the left of this, the E4 inverse is matched up with E4, giving us the identity. So that could be multiplied by E3 to give us E3. And then next over here would be E3 inverse, which would be matched up with E3, and the same thing would occur repeatedly. And then the claim is that this is of form LU. Now to confirm that, you'd have to find the inverse matrices. Well, I can write them down. I'm not going to do the multiplication. I'll leave that to you. But E1 inverse is what you get if you want to undo this operation. The operation was multiply the first row by 1/3. The inverse of that is multiply the first row by 3. Maybe getting a little hard to read. It's 3, 0, 0, and then just 0, 1, 0, 0, 0, 1. Okay? E2 inverse, and let's see if I can write this. I've got to write it pretty small. Hopefully this chalk is sharp. We added the first row to the second, so we're going to subtract the first row from the second. That would undo the operation. Well, there's the inverse. Now E3, when I wrote that down, I obviously didn't write it down correctly. But in E3 we, I was up too close. I saw that as a 0, so all I saw was the identity matrix. Make sure we see that that's a 6. If I missed it from there. Anybody else might miss it. Okay? Well, the inverse of this matrix is to subtract 6. Now, I don't have room to write it in here. I can't squeeze it in, so I have to write it over here. E3 inverse is then 1, 0, 0, 0, 1, 0, negative 6, 0, 1. Okay. And E4 inverse, we just subtract 6/7 of the second row from the third to get back to where we were. So I can probably kind of write that. 1, 0, 0, 0, 1, 0, 0, negative 6/7, 0, and that's E4 inverse. Might be a little hard to read, but I've got my 1, 0, 0, 0, 1, 0 rows there, and that should be 1. And my final row is just the same as this one, but it's got a negative 6/7. And you can think through why that works. Okay, so provided the product of these elementary matrices is lower triangular, we will have reduced the matrix A to LU form. Again, this sequence of matrices times A is what gives us the upper triangular form that we got. so that A is the inverse of that sequence of matrices multiplied by the upper triangular. And for reasons that I explained briefly and explain more in detail in class, the inverse of a sequence of a product of matrices is just the product of the inverses, but in the reverse order so that they would match up in the way I described. And then if these are the elementary matrices that we have here, all of which are lower triangular, then the product should be a lower triangular matrix, and we'll have our LU decomposition. I'll say a little more about LU decomposition, but I'm going to try to get this video and a couple more available because it's been almost 2 hours. And I want people to have these in time to take the test this evening.